And good morning, everybody. We are very happy to welcome Homanga to our. This is the last air seminar for this year, right? We are very happy to welcome Homanga to our last Toronto air seminar for this year. As a quick introduction, Homanga is a PhD student in the Robotics Institute at the School of Computer Science at the Carnegie Mellon University, advised by Abhinav Gupta and Shubham Tulsiani. His research is focused on learning world models for control from passive human videos with compliance guarantees during interaction. He was previously a Master of Science student in the CS department at the University of Toronto here, advised by Animesh, Garg, and Florian Shkurti. And before that, he finished his undergrad at IIT Kanpur. So, Homanga, thank you so much for joining us. We're very happy to have you, and take it away.
Great. Thank you, class, for the introduction. Let me share my screen. Okay. You can see my screen, right? Right, perfect. Yeah. So let's start. I'm going to be talking about auditing machine learning and robot learning for safety and compliance during deployment. And I guess we can take clarifying questions during the talk and maybe leave some of the more open discussions for the end. So let's start with the problem. So the problem is that our AI agents and robots are becoming increasingly good at solving a lot of different tasks, often with precision far greater than what humans achieve in the same task. For example, we have had remarkable progress in the X-rays manipulation of objects in different scenes, legged locomotion in the wild, surgery with the help of robots in a lot of different settings, self-driving cars, and more recently, space robotics. So this actually sounds good. So what exactly is the problem? The problem is that we're not sure whether the agents that we have trained for deploying in a lot of different situations are actually behaving in ways that we want them to. So what they're doing is being good at optimizing for a certain objective. And this objective is usually specified by the human algorithm designer. But we don't have a very good understanding of the exact objective that they are optimizing, whether it is different or very close to what the algorithm designer actually intended. And in the catastrophic limit, they could be optimizing for something that is clearly disastrous to humans, and the humans were just not good in specifying for that behavior. And versions of this problem have been described by different people over the years. And one of the old quotations is by King Midas. We had better be quite sure that the purpose put into the machine is the purpose you really desire. And some familiar examples of this objective mismatch problem is, so when we want the robot to say bring a cup of coffee over to a person, we could specify some objective for this, but the intended behavior is to pass this cup to the person in a way that it doesn't drop on the ground and the coffee doesn't spill on the floor. So while this is the intended behavior, this may not be reflected in the objective specified to the agent, and the agent might optimize for something that sort of optimizes the objective specified, but doesn't achieve the intended behavior. And when this happens, we say that the problem of objective mismatches arise, and we have seen recent news articles that are manifestations of this problem. For example, a self-driving car did not recognize a pedestrian jaywalking, and a Facebook chatbot came up with its own secret language that it was clearly not optimized for. So what is the solution to avoid problems of this kind? We say that the solution is through auditing. So by auditing, I mean rigorously testing failure modes of AI systems prior to deployment, and training such that these failures are sort of less likely in the first place. And this is not new. So this is sort of the de facto standard in industry. For example, in car manufacturing, We have a production phase of the car, followed by rigorous quality testing, and finally deployment. So the structure for the rest of the talk is going to be a framework for auditing machine learning models. This is a paper that I did in my NVIDIA internship. And followed by that, I'll describe a framework for human in the loop auditing of robot learning. So the second paper is sort of a position paper that I published in CoRL this year. So let's start with the first paper, auditing machine learning models. Here, the research question that we ask is, given semantically aligned specifications, how do we check whether the models that we have trained satisfy those specifications? And how do we train models such that these specifications are likely to be satisfied in the first place? So I'll describe semantically aligned specifications in a more detail in the next slides. But to give a sense of it, consider face recognition, which is sort of a problem where we have machine learning models deployed in a lot of systems. And here what we want is we want the person's face to be recognized for sort of different orientations of the face. So even when the face is slightly turned or the background is not exactly what it was during training, we still want the face to be recognized accurately, and not doing so could actually have real life consequences of people being misidentified. So based on this motivation, how do we come up with a framework for auditing these systems? So we describe something called unit test that quantify the verification of these semantically aligned specifications. For example, in the case of the face angle, again, even when the angle of the face is turned by a certain, for example, turned in the range -30 to +30 degrees, we'd want the accuracy of the classifier to basically be above a certain threshold. And in addition to face angle, we could think of other factors in this problem. For example, lighting intensity of the scene. So when the intensity is sort of varied in a certain range, we still want the accuracy to be maintained above a threshold. And we could also have cases of occlusion, where the main object of the scene is occluded by another object. And even when partial occlusion occurs, we would still want the classifier to maintain accuracy above the threshold. So this specification of maintaining accuracy above a threshold is captured by unit test. So to come up with these unit tests for deep neural networks, the main challenge is that they lack an interpretable structure. So since we basically have like an input and a black box followed by an output, it is very difficult to obtain these semantically aligned variations in the input for verification. So we can't actually come up with a system directly that sort of manipulates the image in the pixel space and obtains these different variations for which we could check what the output is. So to mitigate this, we came up with a framework where we use a generative model that is trained on a large unsupervised data set. So what we do is we have a generative model bridge such that the image is encoded by the encoder of the generator, and we have a latent space. And that latent space is sort of shared by the classifier that we want to verify and the decoder of the generative model. So this generative model, the encoder and the decoder, are trained on a large unsupervised data set that is not necessarily related to the task for which you want the model to be verified. But we sort of take the encoder of the generative model and connect the rest of the classifier to that encoder. So in doing this, we essentially have a shared latent space that is shared by the generative model and the classifier. So this is nice because given this, we can actually do some manipulations in the latent space of the generative model, and you don't have to directly manipulate pixels. Based on these key ingredients, we come up with the AuditAI framework. So this framework has a three-party system where we have the training phase, followed by the verification phase, followed by deployment. And there is sort of a bit more synergy between training and verification because, as I mentioned, we not just want to verify models after training, but we want to train them in a way that verification yields a positive result. And we have semantically aligned specifications where we are essentially verifying whether the model satisfies certain semantically meaningful variations in the input. And finally, we have the verification phase occurring in a shared latent space of a generative model. So I'll go into the detail of this. So as I mentioned, these are the three key stakeholders in the framework. So the training phase, for example, we have a deep learning model, FD, and this could be doing sort of any task. For example, it could be classifying whether the image that is input has a person wearing glasses or not. So in this binary classification task, you get an input image and you have to output yes or no, basically, for whether the eyeglasses are present or not. And we also have a large unsupervised data set where we don't have these labels. So the unsupervised data set is for training the generative model, and the data set with labels is for training the classifier that we actually want to verify. And then we have the generative model bridge, where we are basically training the generative model to do control generations. And this is based on a lot of prior work where we have seen that we can manipulate the latent space of GANs, for example, to obtain different structured variations in the output space. And in the verification phase, we have these different unit tests. So each unit test corresponds to verifying a certain semantically meaningful attribute, for example, face angle, or whether the person is smiling or not, or the lighting intensity. And for each of these unit tests, we have a result of verification. So whether the verification is positive or not. And for that, we just plot the verified accuracy. And this verification and the training phase have a bit of synergy in the sense that while training, we would also want to take into account how much the model has been verified and use that loss to backpropagate and update the trained model. So in case the specification is not satisfied, the verified error would be higher than what we desire. And in that case, we would sort of train the model such that this is more likely to be satisfied. And hence the two arrows from training to verification. And finally, we have the deployment phase where we have this specification sheet from the verification phase. And based on this, when a deployment, we are given an input image X. We first of all check whether the range of the latent codes that are encoded from the image with the encoder of the generative model, whether those latent codes lie in the verified ranges or not. So if the latent code doesn't lie in the verified range, then we basically do not use the model for that particular input because they don't know whether it has been verified accurately for that range or not. So you only deploy the model when the latent codes lie in the range that has been verified. So when that is true, we basically check the output of the image, and that is what deployment is in this particular setting. So to discuss the unit test in a bit more detail, what we basically want is we want the classified output to be invariant for a certain attribute. And in this case, the attribute is, for example, a range of face angles. So whether the output is presence of eyeglasses or not from the nominal image. For example, the nominal image is just the pose of the person facing the camera. For the nominal image, whatever is the output, we would want that output to be invariant across variations of the image pose. And once we have this unit test result that is satisfactory, then we get the range of latent code variations for which this essentially holds true. So the classifier output will be invariant for a certain range of latent code variation. And those latent code variations would correspond to the pose of the human face. So for that, we would basically check whether image given at deployment is fitting in that range or not. And if it's not, we would not deploy the model for that range. And similarly, we'll come up with unit tests for these other attributes that I mentioned, lighting intensity, occlusion, and so on. Are there any clarifying questions at this point? Okay. So to basically mathematically describe this, so given this machine learning model F that maps from input space X to output space Y, we can formulate a unit test as a function whose value is less than equal to 0. So capital F is a function of inputs and outputs, and we want the value of that to be less than equal to 0 for all x, such that the encoded value of x is within set S. So EIX is denoting the encoded is denoting the encoding of x with respect to the attribute I. So the attribute I, for example, when it corresponds to face angle, EIX is basically referring to the latent code corresponding to face angle for the image X. So when that latent code is within a range SI in, we want and the output is Y is equal to F of X. We want the value of capital X to be less than equal to 0. So that is how we are specifying the unit test for this particular attribute. So I, as I mentioned, is the subscription for the unit test, and the encoder is encoding the variation of interest. And basically, when this condition is satisfied, then our unit test is saying that the output of the model would satisfy this particular constraint. And now, given such our unit test, we need to answer two questions. One is, how do you obtain the corresponding components? That is, how do you obtain the variations? And how do you guarantee that the unit test is indeed satisfied? So to do this verification process, we basically use a framework called interval bound propagation and a recent modification of that called Crown IBP. So what IBP does is, given some variation in the input space, for example, here I'm showing the variation in Z on the left. So given this region around Z naught, so Z naught is the nominal value of Z, and we have Zi varying within an epsilon ball across Z naught. So given this variation, interval bound propagation basically propagates the bounds of Z naught in a convex manner across the layers of the neural network. So the layers of the neural network are zk plus 1 is equal to hk of some affine transformation of zk. So since we have this structure in feed-forward neural networks, we can basically obtain a convex bound for each successive layer. And finally, we can obtain a bound on the output space. And since the f function for the cases I have described can be sort of described by line. So f is basically whether z capital K, which are the output logits, whether they lie on one side of the boundary or not. So we want the output of eyeglasses being present or not to be invariant to whether zi is within the epsilon ball. So for that, if you look at the image on the right, we obtain this bound across the blue region. We obtain that bound in the output space. And we basically want to check whether that lies on the right side of the black line or not. So what we are checking is whether the upper bound lies on the right side of the line or not, because that is how interval bound propagation works. So we obtain the maximum possible value of f such that the bound is not satisfied. And in obtaining that, we basically check whether the upper bound is satisfying the decision boundary or not. And if the upper bound doesn't satisfy, then all other points don't satisfy. So we can basically then say that the verification process has failed. So one of the issues with doing this verification with the upper bound is that there could be cases when it's actually satisfied and the verification process says it is not satisfied. So in this case, it would still say that the verification has failed, but that is okay compared to the other error where the verification process actually is not satisfied, whereas the output says it is satisfied. So since we have this one-sided error, it's basically okay as long as you don't have the error of the other kind, where we clearly do not deploy a model that has failed. So that doesn't happen through this scheme of interval bound propagation. And the way we modify the original IBP process is we do this entire thing from the latent space Z and not from the pixel space, which is X. So that was sort of the technical description of how the verification works based on interval bound propagation. And this figure is showing the same thing visually. So we have the image X, that is an image of a person with or without eyeglasses, and that gets encoded through the encoder to a latent representation Z. And in Z, we have these different latent code blocks that correspond to different attributes. For example, the orange block is showing the attribute for face angle variation. So when you change the latent code in that range, in the output of the decoder, we would get variations in face angle. And when we have the blue code, it's showing the variation in the expression of the person. So when we change the latent code in a certain range, we would get the output of the decoder to be variations in the expression of the person, whether the person is smiling or not. And again, we obtain these variations through existing techniques that identify directions of semantic change in the latent codes of GANs. And given this latent code, we have the rest of the classifier layers, so FD. So that takes as input the latent code and outputs. So for the output, we have basically we have three different losses. One is the loss of the generative model, and the other loss is the task loss, so the classification accuracy. And the final loss is the verification loss, which I'm calling L spec here. So it checks whether the specification is satisfied or not. And basically, based on all these three losses, we backpropagate and update the model. So LGen can basically be ignored when the unsupervised data set is sort of large, and the generative adversarial network is pre-trained on this large data set. So in that case, we don't need to fine-tune the generative model for this particular label data set where we are verifying this model for. Now we talk of some experiments. So our aim through the experiments was to check whether the verified error rates, how they change with the magnitude of latent perturbations. The intuition is that when the latent perturbations increase, we are essentially effecting more change in the semantic space of the input. And in that case, the verified error should increase slightly, but you don't want the error to increase too much. And we compare this framework. So this framework essentially verifies for semantic change in the latent space of a generative model. And we can compare this directly with pixel perturbation-based approaches. So this is the literature on adversarial robustness, where we make some changes in the input image directly, and we want the output to be invariant to those changes. So how does AuditAI compare to those approaches? And finally, how does AuditAI perform during deployment under domain shift? So when it has been trained and verified on a data set X, how does it compare in deployment on a data set Y that has similar images, but is a different data set? So the collection process is different. So we have some results on ImageNet classes. So we just randomly chose 100 classes of ImageNet, and it has different objects. For example, the class hen has images of hen, and the latent variations correspond to different poses of the hen. And epsilon here denotes the magnitude of latent perturbation. So the absolute value of epsilon doesn't really make sense because it depends on the particular data set. So I have included the percentage change next to the absolute value. So the percentage change denotes the magnitude of perturbation from the nominal value. So when the variation is sort of 25% or 50%, the verified error is still low. But when the magnitude of perturbation increases, then the verified error sort of increases, which makes sense because when the latent perturbation is significantly high, for example, 75% and above, then the generative model is also not accurate. So we basically have to draw a line up to the region where the generative model is accurate. And to do this, we can use a human study, which I'll describe after a few slides. So we don't really care about epsilon beyond 75%. And here I'm comparing AuditAI with the pixel-based variation approach. So for a given verified error, for example, 0.88, we want to check the range of variations that both the approaches certify. So since AuditAI operates on the latent space, the intuition is that a small change in the latent code corresponds to a large change in the output space. Whereas pixel-based approaches, since they verify directly in the image space, we can only have so much variations. And that is basically reflected in the results here, where for the same verified error, we have percentage latent variation that is much larger for AuditAI compared to the pixel-based approach. So for pixel-based approach, I'm basically propagating the output variations to the latent space and comparing them on the same level. And the same is true for another verified error, 0.5, where the AuditAI range of latent variations is 12%. So it essentially verifies over a much larger range compared to 0.14%. So the next experiment is on this CheckSpurt data set that has chest radiographs of 65,000 patients and is labeled with different conditions like pneumonia, edema, fracture. And this data set and labels were collected based on consultation with radiologists in Stanford Hospital over a long period of time. So here the latent variations, the unit tests correspond to different conditions, and the latent variations correspond to different images with a particular condition. So the variations here, the semantic variations here are not meaningful to us because we are not trained radiologists. But here what we have ensured is that each variation basically corresponds to images with a particular condition. So the unit tests are the different conditions, and the variations in the image are variations of images with that particular condition. And based on these unit tests, we can again have latent variations in a certain range. And here again, we see that for variations of up to around 50 or 75%, the verified error is low. And when the variations increase beyond 75 or 100%, the verified error is high, which is okay because we would again draw a line around epsilon equal to 1.5, because beyond that, the generative model is inaccurate. So it doesn't generate realistic images beyond that range. And we do a domain shift study where we have trained and verified the model on the CheckSpurt dataset, and we have deployed it on a different chest X-ray dataset called NIH chest X-ray. So this again has similar images with similar conditions, but it's a different dataset, so it is collected in a different hospital and so on. So here we are comparing AuditAI with the pixel-based approach directly for precision, accuracy, and recall. And here we see that, so here higher is better. So we see that AuditAI essentially achieves higher values of precision, recall, and accuracy on this domain shift study. So this indicates that during training on the CheckSpurt data set, we essentially were able to verify over a larger range of variations, such that during deployment, the test images essentially lie within our verified range of variation. So that is implicit in these results because that is like one of the ways to interpret these results, as we were able to verify over a larger range of variations in the original data set, such that in the test data set, the images basically lie in the already verified ranges. And finally, we have results on the towers dataset, the Flickr Faces HQ dataset. So FFHQ is a set of high resolution images of human faces, and the tower dataset basically has images of different towers in different cities. Okay, see you, Jessica. And And here for the human faces, we can have unit tests like the pose and expression that I mentioned previously. So whether how much the person is smiling and how much their angle is rotated based on the nominal value. And for the towers data set, we had variations in the cloud in the scene, so increase and decrease the intensity of the clouds in the sky, and the brightness of the scene. So the sun is shining brightly or it's completely dark. So those were sort of the variations that we could come up with. And for those variations, again, we had latent code variations in a certain range, where you see that for variations up to around 150%, we have a verified error that is reasonable. And finally, the experiments for how realistic are the generated images. So this experiment is for deciding where to draw the line in the tables that I showed you before. So here we are plotting the percentage correct on the y-axis, and on the x-axis we have different latent variations. And the study essentially had human evaluators, mechanical Turk workers, given a set of images for each of the bars that you see, and they were asked to distinguish between real and fake images for each category. So if they were not able to distinguish, that means the generative model is accurate. So if the percentage correct is around 50%, that means the Turk workers are not able to distinguish real from fake images. And so the generative model is accurate. So here you see that for up to around 50%, on the x-axis, the y-axis is around 50%. So that means for up to 50% variation in the latent code, the Turkers were not able to distinguish real from fake. But beyond that, they were able to distinguish. So the generative model is likely not accurate from 100% onwards. So it comes to limitations of this framework. So one obvious limitation that you might have noticed is that the interpretability of the framework is based on the built-in generative model and is limited by it. So while we have had exciting progress for generative models, it is important to incorporate some domain expertise in the form of human evaluators in the process to mitigate the potential biases that might occur in dataset collection and training of the generative model and so on. So the AuditAI framework currently doesn't integrate human domain expertise in the pipeline, but it is, of course, indirectly used in the curation of the dataset for creating the generative model. So based on these limitations, I'll next describe the auditing robot learning framework, which is a position paper, so it has no experiments, but just the design of a framework, which is probably interesting. So for auditing robot learning systems, we would come up with specifications that we want the robot to satisfy under controlled variations of the environment and task. So the idea is again very similar to AuditAI, where we have some variations, in this case in the environment and the task, and we want the performance of the robot to be invariant to variations in the environment and task. So the aim again is to encode human preferences about what is safe behavior versus unsafe behavior, and what is complying with the preferences of the human. And here I tried to bring in methods from the AI alignment literature and come up with a framework for human in the loop auditing. The motivation for that is that purely didactic objectives, where a human specifies a command, like do something, may lead to unintended consequences. And this is because humans themselves are very unsure of their preferences concretely. So we have a vague understanding of the kind of behavior that you want the robot to have, but we are very bad in coming up with an objective function that the robot must optimize in order to obtain that behavior. So this is the idea of shaping reward functions in reinforcement learning, where the shaped reward function more often than not is mismatched from what we actually want, just because we are bad in coming up with such an objective function that is a distillation of our preferences exactly. And this issue also arises in imitation learning, where we don't have an explicit reward function, but we have implicit data in the form of some demonstrations, which the collection of which is again an imperfect distillation of our preferences. So because of these, it is reasonable to assume that purely didactic objectives where you specify such a function to optimize are will lead to some unintended consequences. Any questions? Great. So what's the alternative from didactic objectives? The alternative is basically learning as an iterative process between the robot and a human. So involving a human in the loop is crucial, because when the robot does something that's basically wrong or not according to the human can give some feedback to the robot, and they can sort of iterate instead of the human specifying a function that the robot optimizes throughout. Based on this, I'll describe the framework for auditing, where we assume we have a pool of human auditors, a bag of reward functions. So these reward functions, so it's not just one reward functions, but a set of reward functions or objective functions more generally, which each of which is probably imperfect, but we have an entire set of them. So we have a distribution over them, and a bag of tasks. Uh, so the tasks correspond to different settings or different environments where you want this auditing process to take place. And here the verification process would be for the human auditors to examine temporal sequences of the robot's trajectory. So given a reward function Ri and a given task Ti, the robot does something, and the human evaluator basically observes temporal chunks of the robot's trajectory. The temporal chunk is basically a set of time steps, for example, which I'm showing on with the rightward facing arrow in the figure. So after observing that temporal sequence, the human auditor would determine whether that particular sequence is unsafe or uncompliant with whatever they intended. And if it's yes, then it would be a check mark, and if it's not, it would be a cross. And this is done across the pool of auditors. So this cross or check is aggregated across the pool of auditors, again, because one human auditor might be not good enough in analyzing whether it's unsafe or uncompliant. So we would want to have some uncertainty over human auditors. That's why we have a pool of them. And basically, that is how we can do the verification process, where the human auditor observes a temporal sequence of the robot's trajectory. But that is not enough. We want to do verified training, where we want to train the robot such that this verification process yields a check and not a cross. So for that, the idea is whenever a human auditor determines a temporal chunk to be unsafe or uncompliant, we swap the objective function from the bag that we had. So if it's a cross, shown on the leftward facing arrow in the figure on the right, so if it's a cross, then we sample a different reward function from the bag of reward functions. It's shown by r hat in the figure. So we have this new reward function, and the robot starts optimizing for this reward function. And the human evaluators check whether temporal sequences of the robot's trajectory are unsafe or uncompliant. And if it's yes, then they again swap the reward function. And this repeats over training. So this is how we can sort of do this verified training process. And finally, during deployment, we would release a specification sheet as before. And here we would have a set of different tasks that we have audited the model for. And for each task, you would have the fraction of satisfaction. So the fraction of the number of times we had a check over the total number of trajectories. And this deployment, this spec sheet would be based on the final model and not the model that was intermediate during training. And it would incorporate the uncertainty in human evaluators through the standard deviation across them for this fraction. So one obvious issue with this framework that you might have noticed is that we are swapping reward functions, and so the process, the training procedure might be unstable. So to do that, we would have to ensure that we are doing this swapping process over sufficiently long periods of time, so that the robot doesn't have this problem of the objective being changed very frequently. So when you have the specification sheet, you would basically deploy the model along with the spec sheet and for all these different tasks or settings. And again, the idea is same. So when the tasks or settings correspond to things like different shapes of the cup, different types of floor, and so on, we would only deploy the robots for which robot in settings where the verification has a high accuracy. So if it has low accuracy on a certain type of cup, we would not want to deploy the robot for that particular setting because it would drop the cup or spill it. So I'm nearing the end of the talk, where here through this audit framework, again, the vision is to make such quantifications of failure modes evaluated by humans the standard for inclusion in spec sheets prior to deployment. So when we have this sort of spec sheet along with a trained model, people know exactly in which situations to use this model and when to avoid using it. And then we are sort of ensured that we at least have some measures of safety and compliance. In summary, uh, we have seen a lot of concerns around innate biases in the AI models that are being deployed in a lot of different settings. And there have been multiple news articles about the necessity for auditing models prior to deployment. So what we observed was that most of these articles don't actually translate to research papers on frameworks for auditing. And hence we came up with the AuditAI framework, where which we believe is a sort of a step towards mitigating this problem and ensuring safety and ethical use of deep learning models prior to deployment. And the framework is by no means perfect. And one of the issues with that framework is that there is no human in the loop. So we can't have an auditing framework that is purely automated. So we do need human in the loop. And I motivated that through the design of the audit framework in robot learning, where we brought in some ideas from the AI alignment community on objective mismatch and came up with a framework where we have this idea of swapping reward functions. And as I mentioned, the framework is definitely not practical for implementation as it is, but the idea again is for the community to think about ways in which you can develop and implement these mechanisms in a more practical manner and have auditing robot learning systems become the norm prior to deployment. So with that, I would conclude, and yeah, happy to take any questions or discussion points. Thank you.
Yeah, thank you, Homanga, for the great talk. Does anybody have questions? Comments, hot takes, discussions?
Yeah, I have a question. So a lot in certifiable, like in classical CS, a lot of work on the certifiability involves some sort of predicate logic or temporal logic. And I actually have some colleagues back at MIT who worked on this in the context of prediction. I'm not sure that I'm not familiar with this line of work, but is this something that people also use in certifiable AI? And what are your thoughts about methodologies that are used in certify or at least in safe AI?
Right. Yeah. So there is a lot of like classical literature, I think, in both in robotics and in certifying systems, for example, power plants or maybe other control systems. And I think one of the issues is generalization. So when you have this logic-based systems, then we need to come up with different predicates for different systems. And that is, I think, a potential issue. But the positive side is that they are basically not prone to all these issues with deep learning models that we have that depend on the data set, for example. So those methods are definitely more safe and more certifiable, but they lack the problem of generalization, lack the notion of generalization across settings. And so I think to mitigate those, people came up with this bound propagation approaches in deep learning, where you basically propagate some bound from the input to the output space that has some guarantees. So I didn't go over the theoretical guarantee in more detail, but those methods in deep learning, they're different from the ones you mentioned, but they still come up with some guarantees, and it's limited to certain function classes, which again is an issue. So I think the idea is to draw inspiration from those classical approaches and come up with approaches that are more relevant for the systems that are actually being deployed now in AI, which are inevitably like deep learning models. So I think that is where I see them fitting in the classical approaches. Yeah.
Okay, thanks.
Hey, Homanga. I have a question about how you propagate. So you mentioned that when you do the propagation, there's a slide. Yeah, this one.
Yeah.
So when you propagate the Z, so does this, so your feature, like your specification Z, like the semantic feature is specified in the latent space. How do you propagate that to your classifier? Do you go to does it go through the generator or?
Oh, so the specification, the capital F, the F is a function of of the latent code and Y, but the specification is actually in the output space because as I mentioned, this is something like we want the output of presence or absence of I classes to be invariant to input variations. So Z, the input is varying in a certain range denoted by SIN, but the specification is actually on Z capital K, where Z capital K is the final logits of the classifier. So this function is actually based on the final logit. So this C transpose Z capital K plus D is actually this line on the right. I don't know if you can see my cursor, but
Yeah, I can see.
the slanting line. Yeah, so that is basically this capital F function. And what we are doing through this bound propagation is when you're varying this Z in this epsilon range, we basically have this nice rectangle here on the left. We're basically propagating the rectangle to the output space and checking whether the bounds on the output lie within one side of the line or not. So if that line in the figure on the right basically overlaps the blue region, that means
Yes.
verification has failed. And if it doesn't overlap, that means it has succeeded. Yeah.
Yeah, so I think I understand that part. I'm just to clarify. So your Z0 is the input feature, right? Or the ZI,
ZI is the input, yeah.
So input. So the input is what is this input? This is the input to the classifier, or the input to or a latent code.
Oh, so the classifier is such that it takes as input the latent code, because from the input to the latent code we have the encoder of the generator. So the rest of the classifier basically takes as input only the latent code and then predicts the output.
Okay, so the classifier takes the latent code as input. Okay.
Yeah.
Thanks.
Yeah. So I guess one of the issues again is that we can't use arbitrary classifiers off the shelf. So we need to have the classifier be such that it has an encoder part and the rest of the classifier. So encoder is shared with the generative model, and the rest of the classifier is actually what we call the classifier because it takes as input the latent code and predicts the output.
Yeah. I see that. That now. Okay.
Yeah.
Makes sense.
Yeah.
Thanks.
More questions?
I got distracted a bit, so please excuse me if that question was asked already. But in several parts of your talk, you essentially refer to, let's say, controlled variation, right? Certification against controlled variation. In some sense, when I think about this, is there a way to automatize getting those controlled variations without essentially searching over a gigantic complex search space? Or is there still a need for humans who say, okay, this is a way in which this model could possibly fail? I'm going to give you an example of that failure. So can you do this without a human in the loop, or do you think that at least for now we need a human in the loop there?
Oh, so for the first paper they described there, the search is automated. So for AuditAI here,
But that is for vision, right? I feel like
Yeah,
vision
that's
is pretty much
what
the only place where we kind of have an idea how to automate this, but right? But I don't.
Oh, right. Yeah, that's true. Yeah. I don't. I mean, so for robotics, the only place I can think of is like simulation, where you have procedurally generated environments where basically that is automated and you can do lots of things. Yeah. But for real robotics, I don't see how we would do that. Even resets are difficult, but I mean, it can be done in some sense. So like people have done resetting the environments where you have, when the object moves out of the scene, some automatic handle pushes the objects back into the scene, and then you do resets. And in a similar way, you can come up with different variations. For example, after an object is done, it's actually pushed out of the scene, and then a different object is placed in the scene with the same automatic arm, for example. But that is again limited to like tabletop manipulation settings and not more realistic settings. So yeah, I don't think we have a good solution for automating the variations in real world robotics. Yeah.
Maybe this is like a bit far-fetched, but if we took the robots out of the lab, do you think we might get those variations kind of naturally, right? Because I think Florian definitely has projects on like driving small robots around in the outside, right? And then you get weather conditions, etc. You get those variations almost automatically, right?
Oh, right, yeah. Oh, yeah. In that sense, you can. So you're saying that we would basically take the robot out in a lot of diverse settings and basically collect those data, and then uh, we have data of the robot in a lot of different settings. Yeah, that makes sense. Yeah. So we'd have to rely on like the weather or other factors in that case. But I think that is definitely possible. I'm sure people do that. In some sense, right?
So then the next question would be like, if you have essentially, that wouldn't be controlled variations anymore, right? That would be the weather you get today, right? And you don't even have access to like the simulation parameter. Would your framework still make sense in that setting?
I mean, in that setting, you can actually control to some extent. I mean, when you're collecting the data, you have knowledge of what the weather is when you're collecting the data. So in that sense, you can have control over what you keep and what you discard in your data set. So, and then the auditing framework would essentially be verification in those different settings. But you would have to make sure that it sort of generalizes somewhat. So if you have verified over weather ranges, for example, precipitation from X to Y, for example, and when it gets a range of precipitation in a subset, then it would still hold true. So that sort of guarantee would come from the auditing framework.
Oh, that's interesting.
Yeah.
Thank you.
Yeah. Any more questions or comments, criticism?
If nobody else is asking, do you think that I get the feeling that when you, not you, but when one in general proposes these kinds of research at many conferences, there's a strong bias against the human element in it. Do you think that the research is kind of limited by the human element, or is it actually made more valuable by the human element in it? What's your perspective on that?
Yeah. I think that's a good question. I've definitely had this question other times I presented the same thing, even in Carnegie Mellon. So it's like, yeah, I think the human element essentially doesn't fit into our picture of automated AI, and so it's more of like a unwanted element which we'd somehow try to get rid of. Like that would be appealing if it's fully automated, but I don't think like for frameworks that essentially checks whether AI systems are doing things correctly, we can actually remove the human out, or we should remove the human out. So I think we should come up with better ways of integrating human in the loop feedback, maybe by drawing inspiration from HRI, how people in HRI, human robot interaction, do things. But I think the human should very much be present in some capacity. And I guess in more like in self-driving settings, you have the human safety driver, for example, in the car, sort of to basically stop the car when something goes wrong. So things like this, and for auditing as well, you'd need the human doing some of the checks, but maybe not in the way I described, where the human swaps the reward function, but maybe in a more efficient way, which I don't know yet. Yeah.
No, I absolutely agree with you. It was more like playing devil's advocate with the question. I don't
Yeah.
actually think we need to remove. Okay, last call for questions. I guess otherwise we are already at the end of the time, but if there's any more questions. If there's questions after the talk, I think Homanga did not get kicked out of the Slack, so
Yeah.
it's always the possibility of contacting him directly.
Yeah.
Homanga, thanks so much. This was very interesting.
Yeah, thank you for inviting. It was fun. Yeah. Nice.
Are you enjoying Pittsburgh otherwise?
Yeah, Pittsburgh is great. Apart from the rain, it's pretty good. It keeps raining, so that's kind of annoying.
Is it colder or warmer than Toronto?
I think it's similar-ish, slightly warmer, probably. Yeah. The weather is okay, apart from the rain. Yeah.
Okay. Then thanks everybody for coming, right?
Yeah.
Everybody have a nice holiday season.
Yeah, happy holidays, everyone.
Yeah, it's the last talk. Thanks so much.
And see you all next year.
Yeah, thank you. Bye-bye.
See you.